discussing a cymbal simulation that I've created to help drummers design cymbals to help them optimize the structural and acoustic properties of a cymbal without having to go through the trouble of manufacturing one straight away. This is I've pretty much started to do this because cymbal crafting is still a very medieval process. So you take this this disc of this alloy, it's copper and tin and silver, and you hammer it out into this flat traditional cymbal shape, and you lathe it, and you do all these things, and you thin it out, and you get a specific tone. And the way that you shape it is just this trial and error changing of the thickness by rolling it, or the hammering pattern on the top to change all these different things. And two cymbals of the exact same brand and the exact same shape and everything will sound a little different. They'll have different overtones slightly, whether it be the decay or the actual notes, anything. It'll be slightly different just due to these small little differences. So I wanted to make a way to simulate that, and I have done that, so that you can model it before actually making it. So it gets rid of some of this trial and error. So pretty much talking about what the cymbal actually is, it's the higher pitched instruments in the drum kit. You got the drums and you got the cymbals at the top. The cymbals are sort of more complex than the drums in the way that you hit a cymbal and it's not one flat note. It's a bunch of overtones and a note. It's depends on the force. It's all these different things. So I've accounted for all that in my simulation. So this is an example of a traditional cymbal smithing hammer that they used to use and still use to this day to hammer the pattern actually into the cymbal. And that's just a set of cymbals as an example. So talking about cymbal anatomy before anything else, the cymbal has three basic portions that we're modeling and going to deal with here. So we got the bell of the cymbal in the center, which is the highest pitch sort of section that you hit. And then you got the bow, which is the center section. It's the lowest volume section, but it's the most common. And then the edge of the cymbal where you crash. Those are kind of the three that I've modeled. And depending on where you hit it, different things will kind of happen. And then there's all these different properties. What are we actually going to change in the simulation? So you've got the diameter of the cymbal, you've got the thickness of the cymbal, you've got the curvature of the cymbal, and you've got the material of the cymbal. These are all things that we're going to be able to change in the simulation and model. So, and then what will that actually do? Actually, I should say, so like if you have a thicker cymbal, it'll be higher pitch. And if you have a thinner cymbal, it'll be lower pitch, which seems kind of unintuitive, but when you think about it, the operating principle of a cymbal is the vibration of the structure through the air. And if a cymbal is thicker, it's usually stiffer. And if a cymbal is stiffer, it wants to return back to its original state faster, so it'll vibrate faster in the air, which creates a higher pitch. So that's one of the many examples of how property will change that. So let's go through the simulation. What does my simulation provide to you? This is what it provides. So this is where all the designing is done of the cymbal. It's this two-dimensional little cut of it, and I've made it so every dimension is a parameter that can be changed. So capital T, for example, is cymbal thickness. When you change that, it'll move the lines apart, making the cymbal thicker as a whole. And you can change all these things. And then the reason why I've done this is the physics applied to a cymbal are not circular. They're not in a circular pattern. They're on one point. But designing a 3D shape is unrealistic. So I'm going to take this shape, which I've designed with these parameters that can be changed, and revolve it into this three-dimensional shape in two separate COMSOL components. So this allows you to design any cymbal shape just by this simple cross-section, and it'll update itself immediately and create this beautiful cymbal shape, which you can use to change and manipulate your sound. So the actual physics of the simulation, so what do we actually do? Well, again, apologies that I can't bring up the actual simulation to show this, but I apply a point load, so this point force on the edge, very edge of the cymbal at one point. 10 newtons in this example. This is a 14-inch diameter cymbal. I apply it there. And there's two portions of the simulation. The first portion is pure structural mechanics, and then the second portion I'll get to later is more complex. So the point load is applied to the edge of the cymbal, and then COMSOL handles the computation of the structural changes after I've, of course, defined the material as this copper and tin alloy, which is similar to modern cymbal materials. So this little animation here is exported from console and shows the 10 Newton force impact on the cymbal. It's scaled up a little bit, about 100 times, just so you can see it a little more. The actual warping itself isn't that large, but this is generally what will happen. So then what's the next step after that? Well, first of all, you can get a lot of information from this. You can get, I have graphs here of specifically here you go. This is the structural results of the cymbal. So you've got the cymbal edge displacement over time with a striking force of 10 newtons. So that'll kind of tell you how much is the cymbal actually displacing, and then that's enough structural data to tell you if the cymbal will break or not. You can get your stresses from that. And then this is the sweep of displacement versus edge force. So this is from 10 newtons to 100 newtons and the actual displacement of the edge. So that's just super valuable data. And this isn't linear. Like there's like random feeling at 1 second it'll be way up here, and then at 0.8 seconds it'll be down here. It just looks linear in this, but if you zoom into these data points, you'll see that. So that's super valuable data. And then going to the acoustic side, so we've got this acoustic sort of simulation that connects to the structural simulation in this air domain. So the air interacts with the vibrating cymbal, and it actually calculates your eigenfrequency and your resonant frequency. So the example I have here, so this is the mode mapped over the cymbal, and I actually got the cymbal to almost perfectly vibrate at a C-sharp 5 note. So that's the resonant cymbal. So, the resonant note is a C-sharp 5, which is, you can see it on the piano here. And then if you take that, so you can also get your acoustic pressure map, which is nice. This is the frequency versus displacement of the edge of the cymbal. So you can see at various heights of the cymbal, it's producing all these different overtones and notes. So what we've essentially done is we've built a cymbal, hit it with a certain amount of force, and simulated its acoustic properties, and can view it over a series of different forces. It is pretty heavy computationally, but it's pretty amazing to hear the property of the cymbal change. So if I was to change the thickness, you would see that resonant frequency go higher. And it takes a while to compute a sweep with this kind of thing, but with some more time and mesh optimization, I know that it can work even better. So again, why is this important? Well, there aren't many softwares that do this, and I think with our modern understanding of acoustics and structural physics, we understand every part of how a cymbal works, and the complexities of the acoustics, and being able to simulate that would allow us to explore new cymbal shapes, for example, or create a set of cymbals that is in a very specific range of notes to match these drums, which is something that isn't done very often. And you could view all types of things with this simulation. You can make, there's an example, these small cymbals called splash cymbals that are typically less than 8 inches in diameter are even higher pitched, and you would see that with this simulation. So I think that this is a very valuable simulation for drummers such as myself to use in order to experiment. The data you can get from this, just acoustically and structurally, is invaluable to designing cymbals. So yeah, it's pretty cool. I'm very excited to show everybody what I've done with this, and I think it's a very useful simulation. So thank you. Thank you for your time for listening, and I will send the console file to everyone as well who I send this to, so that you can experiment with it yourself and try and design some cymbals. Thank you.